So, good morning. Today we will discuss the two independent sample t-test. So let me just write that as a title here. Two independent sample t-test. Two independent like that. Sorry for this. I am not yet savvy on using the independent sample like that. Sorry for that. T-test. So there are two samples that you are testing. T-test, and your the t-test tests whether the means of the samples are statistically equal or not. So it's a simple, it's a test of quality of means. Two independent sample t-tests. There are at least three t-tests rather. One sample t-test, the two paired t-test, the two sample paired t-test, and this one. So we're focusing on this one. There are two samples and then t-test, two independent sample t-test. And so it's a very simple test. It has a measure of the separate, it comes up with a measure of the difference of means, and that difference has a statistical distribution, and when it has when a difference in means has a statistical distribution, then if it's rare or if it's common to arrive at your measure, at your t value, right? The difference in mean. If it's rare, or if it's rare to arrive at a higher t than your t, then you should accept your results as valid. That your results, that your means are not equal. Usually, you're comparing means that are not equal in the first place, right? Well, you're trying to test them statistically, right? To test the inequality statistically. So what is that measure actually? You just there's a t, the t value. What do you call the t value? It's just it's a ratio of the difference in means over the standard error, right? How is that so? Conceptually, let's say here is two sets of experiments. 1, 2. This is the number line of the results of the experiment. So this is 0 to infinity. And one set, let's say there are 5 observations, for example. So let's say the red observations are here. Well, this is by chance. So they're all over. Well, it spans the number line that I just drew. That's the observations of your first sample. Yeah. This is the number line. And then you have your second sample. You have also the observation. Maybe here. 1, 2, 3, 4, 5. Yeah. So if you have such a result of your two samples, the observations are laid down over there. By observing them, you can say that they're mixed up, right? One is just mixed up with the other. You can't distinguish one group from the other. Yeah, by just observing the results or the measurements, you can just yeah, intuitively you can say that one group is different from the other. But if you have another experiment, which you have another experiment like this, and where the results are really separate, like distinct. One, there are observations for the red sample is here. The observations and the green samples are here. Then you could immediately say that this group are quite different, right? They have different means and they're quite separate from each other. But here, the means might, in the first experiment, the means might be different, but the individual observations are actually very mixed up. For example, let's say the mean of the red group is just right in the middle. Well, I'm just guessing, I suppose for him, because this is the middle of the range, more or less the middle of the range of observation. So the mean, maybe, more or less, that's where the mean is located for the red group. And for the green group, it's almost the same. That's also here. That's a mean of the observations of the green group. Here, in the second experiment, the mean of the red group would be in the middle. Oh, well, sorry for that. I can, yeah, and the mean is there. And for the green group, the mean could be here, right? So what you can see from this illustration that the means are far apart. They have a very large mean difference than the first experiment. Very small mean difference, right? Like this mean difference, very small, and this is very large. So if you're comparing when comparing group separateness, like this green and separate from these, normally intuitively compare their means, but that's not enough. You should also compare how the individual observations of the groups are separated from each other, right? Or one group is separate from the other. I'm talking of the variance of one group, the variance of the other from the mean, right? For example, in the first set of experiment, we have like the variance is big, right? Here. Sorry. The range, at least for the range, we're not, you can more or less intuitively see the variance by looking at the range, right? The variance, the numbers, the range of numbers are so varied. So you have a large variance, right? From that to that, from the smallest to the highest number. And for the green group is from here to here. So the variance is quite large as well, right? I mean, here in the second set experiment, the variance of the red group is from here to here. So it's quite small, smaller than the first experiment. And from the green group is like that. So the variance is quite small, right? The variance is quite small. So if you can see, not all, and here the members mixing up with each other, the red group, you can see that the means are not only are very close to each other, but the variances of are very wide. They're actually overlapping each other. The variances of each group, overlapping. But here you can see that the mean difference is quite wide, and the variance of each group is quite short, or quite short. So intuitively we can differentiate it by But look at their variance, right? Look at the means and their variance, the variance of the groups and their mean, the mean difference in the variance. You can have a measure of how separate they are. This, one might say that this is one just one group. This first experiment is just one population or one group, one population, one population. It came from one population because they are mixing up, and these are separate populations. Because separate the second separate, yeah, separate populations or different populations, different means. But here you can say just one because they're mixing up. The members are mixing up together. And here they're quite separate from each other. Means are quite separate. So an intuitive measure could be the measure of how separate groups are would be the ratio of the mean differences and a measure of the variances. Called the standard error. All right, it's related to the variance. Yeah, right. Standard error. So how is that done? Well, you can operationalize by really computing for mean differences and the standard error and get the ratio, and that's the t. That's the t value. So that's how it's done. So let's go to phase 2. So we have the t, which is a measure of the how different are the means. So, well, it's just the, as I said, the ratio of the means of one group. This is the t. The standard error is computed like this for samples that have equal number of members, equal number of objects, equal number of observations, n being n1 plus n2. I mean, the members of n1 plus the total, and the total number of observations of group 1 and group 2 plus n. This is the numerator here is the standard error. So, so as I said, it just measures, mean differences. It is large, and divided by the standard error. Standard is just a standard deviation over the square root of n. So t measures how many times mean differences is greater than the standard error. Yeah, so if it's very big, then chances are the means are very separate, and your standard error is very small. Well, if there's since this is just a division, this the numerator is a big one and this is small one, you have a big number. Well, if you have a standard error that's big and you have a small mean difference, I mean, they're very close to each other, the means are very close, so you have a very small t, or which means a very small t, chances are the differences are not significant. It also means that your observations are quite intermingling with one another. You're overlapping with one another because of the very large standard error, right? I mean, it means you can distinguish groups by just observing the data, right? Because some members of group 1 are within the range of group 1, there are also members of group 2, and within the range of group 2, there are also members of group 1. So they are what you call, I just call it quote-unquote overlapping members of group 1 and group 2. That's the case of the page that I saw here. Here, then the first experiment, they are actually all the range of let's say for the red group, the range of observations quite include a lot of observations of the green group as well. So here in the first group, and also with the green group, the range of the green group quite include a lot of remaining red group. So that's what I mean by the standard error is quite very big. And if you have a very big standard error here, then chances are their t is very small, right? And would be smaller if you have a big number here. Of course, you should look at the mean difference first. If you have a big mean difference and have a small standard error, then chances are your groups are separate. But you have a small mean difference and a big one, the chances are your groups are not separate. Right? So you have the t, and it has a distribution, the t distribution. You can look it up. So we're given your t, you know the probability of anything less or anything of any t less or more than your t, right? Since it's a probability distribution, right? We have a t distribution like this, so maybe like that. So if you have a t, you have a t here, your computed t, then you know, since it's a distribution, you know that anything less than your t or anything more than your t, you know those distributions because it's just the cumulative. Yeah, is this shaded areas is just 1 equal to 1. So if you have your t here, you know your probability of t anything less than your t, because anything more than your, these are just complements, right? If this is 0.05, then that is 0.95, or if that is whatever number that you get, and the other side would be the complement, all sums to 1. So that's it. And then you compare your t with the known. Since the probabilities are known distributions and they're already tables, right? Or you can, yeah, the software can just compute it for you. It's probability of your t, probability of t greater than your t, or the complement of it is t less than your t. Yeah, usually it gives the probability of t greater than your t. So if you have a t like I don't know, like 2, whatever, 2.5 here, then it gives you the probability here it might be less than. Usually it's less than. Not sure, it could be less than 0.05. Usually with large t, usually like that. So 0.05 is probability, but it really depends on your t carb. There are many t carbs depending on the degrees of freedom. Yeah, right. Degrees of freedom. Degrees of freedom. So that's how it's done. T-test, hypothesis testing. It's easy because you have a known distribution. That's the t-test. Let's illustrate this with a I'm screen sharing, so I can open my page, for example, to get the t-table, for example. Oh, all right. I think it's recording. This is a supplement of the 2 independent sample t-test. Because I noticed that there's an error. There are some, errors, or what you might say, because of it's not actually an error. But I was not. I thought I was showing the table, but I was not showing the table. So when you are hypothesis testing, you inevitably consult your table of critical values, right? So let me, for example, if you have all this, all right, I have 20 observations in all for you might imagine there are 10 in sample 1 and 10 in sample 2, 10 observations sample 1, 10 observations on sample 2. So in this case, you have 20 observations and your degrees of freedom should be 18, right? So you set your significance level maybe at 0.05, and your critical T should be consulted in the table. Your critical T should be what? So let's consult our table. If you have these givens, your table, it's your. All right. Let me just committed the mistake of. Let me just share my screen. Sorry for that. I have a cold, so your critical for that. This is your T table, critical T table. For the cells are the critical values of the T, and the columns here. The column level gives you the probability of this T to the right of this T. The cumulative probability to the right of these T's that are in the cells, right? So let's say if you have 20 observations, you have 18 degrees of freedom here, and you set your significance level of 0.05. Your critical T is 1.734 there. So 1.734 is your critical T. Let me have my, instead of drawing like this. Okay. So if you have your 20 observations, 18 degrees of freedom, then your significance level is 0.05. So your critical T is 1.734. You set that yourself, no? That's your, what does it mean? Well, the probability of any T higher than 1.734 is less than 0.05, because it always decreases to the right, since the sum is 1. So if this shaded area is 0.05, then given our degrees of freedom, that should be 1.734. So anything to the right of that should give a lesser probability, lesser than 0.05, because it's always decreasing, right? From 0.05, because the total area of this should be 1. So you know that smaller and smaller area is added once to the right of 1.7304. So if you have a T, for example, if you have a computed T in your experiment, that's for example 2.0. So you know that 2.0 is to the right of 1.73, maybe here, and of course that the probability of anything higher than 2.0 is less than 0.05, because 0.05 is already way up to the left of that of 2, right? So you know that if this is 2, then you know that this is less than, this area is less than 0.05. All right, that's what it means. My hypothesis testing. If you know a T, if you have a T that is greater than 1.734, and given these facts about your experiment, you know that it's rare to get a higher t. It's very rare, it's low probability. So you, in this case, you actually you have enough proof of your t being high enough, which means your mean differences are high enough, are high and high enough to be different from zero, right? Because, you know, your null hypothesis is that the mean difference is zero, or which is about the same thing, x1 bar. This is x1 bar. Oh, sorry for that. Is equal to x2 bar. That's your null hypothesis, or the mean difference is zero. That's your null hypothesis. And if you have a t value that's high enough, where anything higher than that gives a low probability of occurring, then you accept your results to be very significant, meaning your unequal means are significant, right? Significant t-test result, right? So that's how it's done. Yeah. Well, it depends on your significance level, right? If you are very stringent, want to be very stringent or very strict, or very, not risk-taking at all, you're very worried about risks for experiments, risks to be wrong, then you can have a very low significance level, like 0.01. It's also valid. So you set the cutoff t to be 2.552. That's for the degrees of freedom rating. So anything you should get a t. If you get a t higher than this, then your results are significant. But if it's lower than this, your results are not significant. Right. Okay. Thank you. That's about the t-test.